Hello, welcome to the Data Platform Virtual Summit 2021. My name is Pedro Lopes. I'm a principal architect in the SQL Server team, and I want to talk to you about our intelligent database story. Specifically, how you can get started scaling up your workloads today and in the near future by using intelligent performance features that we ship in the SQL database engine that powers both Azure SQL and SQL Server. We'll start with a brief history of intelligent database, how you can get started using the technologies available to you now in both Azure SQL and SQL Server, and then we'll spend most of the session looking at what's coming next: query store hints, CE feedback, and PST optimization. As we get started looking at intelligent database and how we got here and how you can get started, we see there are already a number of features available to you in terms of intelligent query performance. And we see the family of adaptive query processing features that we've made available back with SQL Server 2017 and simultaneously in Azure SQL Database. And then later in SQL Server 2019 and again in Azure SQL Database, we've added more scenarios to what is an overarching theme of intelligent query processing. Now, the principles that guide us through this journey are three, and they are simply stated as this. These features and the benefit coming from these features needs to be available by default when you move the database to the latest compatibility level. So it's not enough to move your database from an older version of SQL to Azure SQL Database or to a newer version of SQL Server. You need, at a later point in time, according to the recommended guidelines that we have that are very tangible for you to make this move of upgrading DB compat level, only then will these features become available. They also need to deliver broad impact that will really improve performance of your existing workloads with minimal or, for the most part, with zero implementation effort. And I say minimal because if you notice there's an asterisk there in approximate query processing, and that's because approximate count distinct is a new transact SQL function, and as such, for you to use that particular feature, you actually need to have a code change. But for everything else, it's zero code changes for you to take advantage of these features. And the intent is that those critical parallel workloads need to improve when they're running at scale, whereas you add more users, and still remain adaptive as data changes in your underlying database. And so the session today, although it's not about intelligent query processing that we've done in the past, and you see here one example of Itaú Unibanco, which was one of the customers that jumped on SQL Server 2019 when we released it. And you see here that without code changes, they were able to have significant performance improvements. They were able to get their applications to run faster with minimal downtime, and again, zero implementation effort from a code perspective, from an application perspective. And even the example of the Mediterranean Shipping Company, where a combination of several intelligent query processing features in SQL 2019 plus other features that were debuted in SQL 2019, like optimized MTB metadata, they were able to just increase the performance of their applications without any code changes. Like I said, this is not about what we've done before in intelligent query processing. This is about what we're going to do next and what scenarios we're going to tackle next. So to know more about each of the features that we've seen in the previous slides, you can go to this short URL, https://aka.ms/iqp, and you can actually run demos, self-guided demos, either scripts or as Jupyter notebooks, in this other URL there, aka.ms/iqp demos. Now, let's move on to the bulk of our session today. And we'll start with query store hints. Query store hints are now in public preview in Azure SQL Database. As we've seen with previous features in the feature tree, everything that I'm going to discuss today will eventually make it to a vNext of SQL Server. So let's first understand what are query hints and why this scenario was needed to ensure that we can use query hints in Query Store. Well, ideally, the query optimizer will select an optimal execution plan or a good enough execution plan for every given query. But we also know that under some certain conditions, that may not happen. And it may be a mix of how the query is written and some heuristics in the optimizer and data distribution. So sometimes a developer or a DBA must manually optimize a given query. And one of the ways to do that is specifying query hints. Those are specified using the option clause, as you see on the screen there, and they can be used to influence how the SQL engine will optimize a given statement. For example, in the query on the screen, you see that it was necessary to add the option recompile on every single call to this query, and to also disallow batch mode on row store, for example. And applying query hints today can really help you provide very localized mitigation for performance-related issues. They do require you typically to rewrite the original query code by adding those hints. Another option that's also somewhat cumbersome is to use plan guides to add those hints. The common feedback is that plan guides are complex to use, complex to manage and track. And so we wanted to look at an easier option that's more modern to allow us to hint queries if needed. And so we introduced Query Store Hints. This feature will provide a simple method for changing query plans through hints without you having to change your application code. And sometimes application code is actually generated on the fly by some ORS, for example. So it's even harder in those cases to be able to change your code at the source. Now, the feature Query Store Hints leverages Query Store, which is on by default in Azure SQL Database. And this greatly simplifies getting insights into how workloads are running. Now, how can we use Query Store Hints? The first step is to find in the Query Store the query ID of the query that we want to modify. And that can be done, for example, with this query you see on the screen here. Looking at the sys query store query text and having a where clause that has a partial of the string that is in a transact SQL query. And I get back a result, for example, this one. The query ID is 46,006. Okay, I have the query ID now. Step 2 is to execute the SP query store set hints with the query ID and the query hint that we want to apply. In this case, I'm applying the query hint hash join, meaning that I'm forcing all joins to happen with a hash join type. I can actually use more than one hint. I can set multiple hints using the same store procedure, but I do need to pass as a parameter a string that is made up of all the hints that I wish to apply to that given query. And so if I need to change any hint in the future for this query, I need to, for example, add a new query hint. Then I need to use this same string and still add the new hint I want to add. Conversely, if I want to delete a hint but I leave others, I again need to execute the store procedure with a new string with the set of hints that I want to use. Okay, so what are the use cases for query store hints? Maybe I want to recompile a query on every execution, or I want to set a specific degree of parallelism, Or like we've seen in the example before, use a hash join instead of a nested loop that would be chosen by default for a given query. Or I even want to force a specific compatibility level in the query, not in the database, while keeping everything else at the default compatibility level of 150 if we're talking about SQL 2019 or Azure SQL Database. The query store hint, as you've probably gathered by now, will support query level hints only. Those were in the examples we've given. And that's by design. In this first version, it's only query level hints. The second one is these hints are persisted. So they'll survive restarts. They'll survive failovers. They also override any hard-coded hints that you've had written down in your queries or plan guides. In other words, if you add a hint through query store hints, they will supersede any hints that you have written down in your code or have otherwise added as a plan guide. Now, there may be a case where you're adding a hint that contradicts what's possible to execute the query. If you are doing such a thing, then we will not block query execution. The query store hint will not be applied because the ultimate goal is to still allow the query that you've issued to actually be able to execute. So the syntax, as we've seen, is to set the hints query ID and query hint as a string. The behavior is simple to understand. If there's no query store hint already, then a new query store hint will be created. If there is a query store hint, then when you issue this store procedure with a given query ID, the new string will override any previous hint that was there. So remember to always look at what you have today in terms of a set hint in query store in case you want to add more or remove some. You still need to issue what is the final state for the hints to apply to that query. Now, if a query ID does not exist as expected, we will have an error saying that we couldn't find the query ID. Now, the other part of the scenario is that at some point in time, through some improvement in the engine or some other aspect, you want to remove a query hint. The interface for removing hints for a query ID is to run this other store procedure, sp query store clear hints, and you just have to give it as a parameter the query ID. In this first public preview, we will allow you to use a number of hints, like for example forcing a specific join type, or the fast hint, or force order, but also if you want to influence the memory grant, or issue a specific max DOP, or even issue recompile like I mentioned before. There are a couple of hints that are not supported in the preview, but we are still targeting them for GA, which is optimized for a given value. Remember that optimized for is already supported in the public preview, it was in the previous slide, and also max recursion. We have a few other hints that are unsupported and not planned for GA. For example, use plan, because you can use the query store plan forcing capability through SP query store force plan, and use hints that are consumed in a very early stage of compilation before the query plan is even formed. So, for example, deferred compilation table variable or disable T-SQL scalar UDF inlining, those are so early in the compilation phase that we are not able to support them after the fact through query store, after the compilation has been completed. And for beyond V1, we want to expand the scope to apply query hints to incoming queries that have not yet captured by query store, for example, looking at patterns, or to apply parameterization to queries that force a specific form of the plan, but also to add table hint support, like forcing an index or issuing a force scan or a force seek. As I mentioned, this feature is now in public preview in Azure SQL Database. And if you have any feedback for the team, you can use that email on the screen there, qshintsfeedback@microsoft.com. CE Feedback is a feature that's going to be in public preview later in calendar year 2021. CE stands for Cardinality Estimation. And Cardinality Estimation is the process by which the query optimizer will know or estimate the number of rows coming through a query plan from the time they are read from a scan or a seek, for example, flowing through aggregations and filters and other operations until we produce the intended result set. Knowing the number of rows or estimating an accurate number of rows is fundamental for a good enough query plan to be produced. Cardinality estimation is primarily derived from histograms that are created when we create indexes or statistics, either manually or automatically through auto-create stats or implicitly when you create an index. CE models are based on assumptions about how the data is distributed and the expected usage given a given query pattern. However, this session is not about going deep into the cardinality estimation process, but it is a thoroughly documented piece of internals that you can go and read more about in that short URL, aka.ms/SQL-CE. What's important to retain here is that the database engine sometimes cannot accurately calculate the cardinalities, the estimated number of rows flowing. And so, if the cardinality estimation process makes incorrect assumptions, those may cause suboptimal query plans that will be perceived as poor query performance. And so what we know is that today one model does not fit all scenarios. That's where CE feedback comes in. The intent of CE feedback is first and foremost to look at scenarios that can reduce the upgrade friction and risk related to using the default cardinality estimation, especially when you are moving from very old versions of the SQL engine, like 2008 or 2012, all the way to Azure SQL Database or to modern versions of SQL Server. Now, you shouldn't have to be an expert in cardinality estimation. Ideally, you shouldn't have to care about these concepts. So what the feature will do is that we'll learn which model assumptions are optimal over time, and then for repeating queries, apply the historically correct assumption. The intent is to automatically apply the optimal CE models based on the workload characteristics, based on observation of when row estimates are significantly skewed compared to the actual row counts flowing through a plan. So the CE feedback will identify which model-related assumptions are at play in a given plan, will evaluate if they are accurate enough only for repeating queries, and the accurate enough means looking if an assumption looks incorrect based on the comparison between estimated number of rows and the actual number of rows flowing through the plan. And it will verify, tangibly verify, if a different model-related assumption will help. And if it does, then we will replace the currently cached plan with the modified version that uses a different model assumption. This will address a number of scenarios that were not handled yet by other intelligent query processing features that we know can cause those perceived regressions when moving from very old versions of SQL to newer versions of SQL. And those are the independence and correlation assumptions, the join containment assumptions, and row goal. Now, again, these are all thoroughly documented, but we'll go into a bit more detail in the next few slides. The scope of the feature C feedback is not to become a new CE. Like I mentioned a minute ago, we know that one model does not fit all scenarios. And so the cardinality estimation process, feedback, will apply feedback when you have those significant model estimation errors. It needs to be orders of magnitude off the comparison between actual rows and estimated rows. It will also only be applicable for cache persistent plans, for repeating queries, and DML in this first version. Now we will do the adjustment of these model estimation through the use of use hints, query hints, and those are totally documented. And we will use the hint support in Query Store that we have discussed before. One piece of different behavior related to hint support in Query Store here is that C feedback, should it find that a hard-coded hint is present in a given query, we will not touch that query. And that's because if you have a hard-coded hint, the assumption is that the developer has done so intentionally, and so we will not risk enacting a change that is contrary to what the developer has set in the code. So we will honor any hard-coded query hints if they are used. This is different from when you yourself are, as a user, adding a hint to a query in Query Store, because those will supersede hard-coded hints because it's still a user action superseding a user action. Different from a system automation superseding a user action that was purposely set. And like I mentioned, only verified feedback is persisted. Now this means that when we are using a non-default model assumption through a hint, if that next execution regresses, we will back off. It will go back to the defaults that were being used before, and you've only, let's say, wasted one execution. If, for example, that execution that we are doing with a separate model assumption ends up being a long-running query and you have to manually stop and roll back that query, that will also be perceived as a regression and we will also back off. Let's look at the precise scenarios that we are tackling with CE feedback. The first one being correlation analysis. Correlation means the analysis of multiple predicates that belong to a single table. Look at the query that you have on the screen there. We are selecting from the person address table, and we have two predicates looking at for specific values in two columns, state, province ID, and city. When correlation is used, what cardinality estimation feedback will attempt is to move the correlation to the correct direction one step at a time, based on whether we have an underestimation or an overestimation from the default. It's important to understand what the defaults are depending on the version. So correlation analysis can be using an independence assumption. That is a default for CE70, for let's say the legacy CE. And it basically assumes that even in a given table, every single column is completely independent from the other. This assumption changed back in the time of SQL Server 2014 to partial correlation, which is supposed to be more lifelike. Looking at the table person address, we know that should be some correlation between the city named Dallas and the state province ID 9. Those are not fully independent, much as a zip code or a postal code is not completely independent from the city name. So partial correlation became the default for CE 120 and above, the so-called new CE. There is, however, another type of potential correlation, which is full correlation, and that is not a default, but it can be used today through trace flags. 9471 for newer CE, 4137 for CE70, but you can do these changes or enact these correlation changes at the query level using use hints, again, fully documented. Now, how will this correction take place? Well, this is for repeating queries, so we will be looking at the actual number of rows flowing through a plan as they relate to the estimated number of rows flowing through a plan. If the actual number of rows is higher than estimated, given the default is partial correlation, we will jump to use full correlation. If the estimated number of rows actually is higher than the actual rows, then we will jump to full independence and verify if this helps. If it does, it becomes persistent, as I mentioned. The other scenario is row goal analysis. Row goal is a default optimization in the engine. And it's a default that happens if we are in the presence of a specific query type, query profile, if you will, query pattern. And the query is that needs to have a top keyword, fast, in, or exists keyword in it. Much like the query we have in the bottom of the screen there. Select top one from a couple of tables. Now, what this optimization does is it will calculate the number of rows that need to be read to find the required, in this case, top n rows, or fast n rows, for example. And then based upon it, we'll try scanning as fewer pages as possible to produce the required number of rows. However, if the data distribution is off, if we are looking for a rarely occurring value, then it may happen that SQL will scan a lot more pages than were estimated, and this is when row goal becomes inefficient. So when we detect that this has happened, we will disable the row goal, which was likely using a scan, and we'll enable a seek instead. Now today we can use hints like for seek to work around this. See feedback will detect and automatically correct these scenarios. The other scenario is containment types. Containment types can be one of two. It can be simple containment, which was the default in CE70, was a default in the so-called legacy CE. And overall, it means that users always query for data that exists. That was the assumption. So it works by estimating the join selectivity. So there's a join present. Containment types are join containment types, if that was not clear. So we'll use the filter estimates first, meaning there's a query with joins and where clauses. And so the filters are estimated first and then the joins. Base containment, however, which is the default for C120 and above, starts with the principle that queries may not always produce a result set. In other words, the users may query for data that actually does not exist in the table. So we flip this into becoming base containment, which assumes that first we need to estimate the join cardinality and then apply the filters. In a query like you see on the screen here, where you're selecting from the fact currency table and joining with the dim date table, you also have a where clause that has predicates over both sides of the join. You have one predicate, month, number of year, that relates to the dim table, the dim date table, and you have the currency key and the average rate that belong to the fact currency rate table. So how does the containment analysis work? Containment, as I mentioned, only applies to joins, and only when those joins have filters also applied below the join. It's exactly what we have in the query on the screen there. If the incoming join estimates are good enough, so the rows flowing to the join, they are accurate in what relates to the comparison between actual number of rows and estimated number of rows, but then the outgoing estimates are bad, meaning the estimated number of rows going out of the join as they compare to the actual number of rows observed going out of the join are very skewed, they're bad estimates, then likely we're looking at the containment model issue. And so, because we know what the default is for a given cardinality estimation version, we will simply recommend the opposite containment level and see if that one helps. If it does, then again, it becomes persistent through the query store hinting mechanism, and it will effectively have fixed the estimation issues in that query. Let's look at a demo for this feature. For this demo, we are using the TPCH database. As we discussed, query store is a fundamental, so it is turned on by default in Azure, and in this case, I'm just going to ensure it is turned on. Also, notice that I'm using very aggressive settings for the query store. These are not the defaults. These are just for the sake of a demo. Do not use these settings in production. All right. Then just to make sure that I have a clean demo environment. All right. And then I'm also going to set automatic tuning. It is a good practice to enable automatic tuning in databases because it is the last line of defense in case a regression happens. Now to the main part of the demo. I'm going to set up a next event capture, and it will have these two extended events. One is query feedback analysis that will display the information of the model assumption hints that may be needed for this query that we're going to execute, and then query feedback validation, which will fire if the query hints that are used are validated and then persisted in the query store for subsequent use. So let's set up this X event session. It's already here, see feedback. I'm going to start it. And then I am going to watch live data. All right. Then the first thing I'm going to do is execute this query a few times, just to ensure that I have enough queries to make it, let's say, a repeatable pattern, which, as we discussed, this is for repeatable queries. I am just going to ensure that the data gets flushed into the query store. This is, after all, a requirement that the data is in the query store so that it can start getting analyzed. And we also mentioned that this is only for cached plans. So if we look at the plan cache right now, I see that I do have a compiled plan that was used 15 times in this case, and it is for the query that I was running. If I look at the query plan right here, I will see that it is a merge join between a clustered index seek and another clustered index seek with a sort in the middle. All right. Then the next thing I need to do is execute the query a few more times. And the next time I execute the query, this should do the C feedback analysis, meaning that it should ensure that now this query is eligible, it's been executed enough times, it is of a pattern that is recognizable, and therefore it will be analyzed by the query feedback. Now, if let's expand this a little bit. we see that the feedback hint that is being suggested is to assume full independence. And I do have here the query ID in the query store. All right, then the subsequent execution of the same query will trigger the verification stage. Let's actually, at this point, bring in the actual execution plan so we see if anything changes. So this is piggybacking on the executions that my application is sending in. So as I execute this again, it has validated. And let's look better at the validation data. So I can see here the original CPU time, almost 3.5 seconds. And I can see here the new CPU time, 2.5 seconds. So it is indeed better. We see here that it's almost 800 milliseconds faster. And if you look at the plan has changed to a nested loops. Because it is nested loops, it doesn't require sorted inputs. So one of the clustered index seeks no longer has a sort on top of it. And this query is indeed better than its original. Now, as we explained, if there were less rows than estimated, which was the case here in the initial plan, that's why we went to full independence. And this is, we can see that it's indeed better. If there were more rows, more actual rows than estimated, then full correlation would be better. And this was not the case. So we moved towards full independence. Now, if we run this again a number of times, we will see that the execution plan changed, and it's all changed to the nested loops that we deemed correct or better than the merge join, and it is persistent. So no code changes. The C feedback detected an opportunity to improve based on a better or a more applicable model assumption, and that's what it went with. Now we can see, using these catalog views, that the query ID 2 has now been set with the full independence use hint, and the source description is C feedback. It's a feature that has indeed persisted this hint. The other possible value here would be user, if a user had set the hint explicitly through the query store hinting mechanism. And we also see here that in the interim, for the plan feedback itself, we see that indeed verification passed. And so we know that this has been persisted in the query store for subsequent uses, and we've seen that those subsequent uses really happen. There are a number of supportability artifacts already created. You can look at the sys query store plan feedback. This will be changed to actually DMV with a slightly different name when we move closer to GA. The intent will be then to have a JSON that will contain all the info on the validation and the feedback analysis for any given query ID. And it will give you the current state of that feedback loop. And we also have the extended events that we've seen today, which are the query feedback validation that will show you the hints that will be submitted for validation, and the query feedback analysis, which is the hint that's generated from the feedback analysis. As I mentioned, this feature will be in preview later this year, and you need to follow the Azure Updates blog and stay tuned, because we will announce there when the public preview is available. And should you have any questions, any feedback, please use the email you see on the screen there to provide feedback for the team. Parameter-sensitive plan optimization is the other scenario that we will discuss. It will be in public preview later in 2021, and it derives from the definition of a problem, the parameter-sensitive plan problem, also known as parameter sniffing problem. It refers to a scenario that derives from the fact that SQL by default will only keep one cached plan for a parameterized query. However, if the first time that parameterized query is executed and the plan is created and cached is not representative of most of the execution types for that query, then you are indeed stuck with the first plan that may not be optimal for all possible and recurrent incoming parameter values. So consider a store procedure in a real estate database that lists the product or the property portfolio per each agent ID. When the store procedure is first called with agent ID 4, it produces this very optimized query plan that returns 3 rows. And you can see by the query time stats in show plan that it doesn't even take 1 millisecond to execute. This was the first execution of that store procedure, and so this plan is now cached for every subsequent execution of the same store procedure. Then the procedure is called with an agent ID 2. As you see here, the same plan shape is used. However, instead of 3 rows, like executed and they were estimated for the initial plan, now almost 5 million rows are returned. And we can see the CPU time that takes almost 1.5 minutes of CPU. And it takes almost 4 minutes overall to execute. Notice even the yellow sign on the sort that means that the sort is spilled. Well, consider that the previous estimations were on 3 rows, and even the memory grant for this query was based on the estimations. And now a lot more rows are being used, and therefore memory that was attributed for this plan, so the memory grant for this plan was not enough. A new compilation, so a recompilation with agent ID 2, however, yields a different plan, as you see here. For returning almost 5 million rows, a scan is much more appropriate for the query in question. And yes, the sort is still present. Notice that the sort is now accurate in terms of the estimated rows versus actual rows. Yes, it still has the yellow sign, but this is just for the first execution, because consider that, for example, memory grant feedback is being used in modern SQL systems, and therefore it will take care of this issue in the next subsequent execution, and then we will have a plan that is completely optimized for returning 5 million rows. Also notice in comparison the query time stats for this second case. We have roughly half of the CPU time being used, roughly half of the elapsed time as well, just by the fact that we were able to get a more properly estimated plan for this query. Now today there are a number of workarounds for this scenario. We can recompile all the time by using the recompile hint. You can generate, let's say, more generic plans by using optimize for unknown. You can even use nested store procedures, where you have one, let's say, mother store procedure that then calls child store procedure based upon certain parameters. And then each of those child store procedures will have its own plan, and therefore that's one way of addressing it. Or you even bite the bullet and state that you know which is the parameter that's used most often that produces a given plan that's good enough for most executions, and you can use the optimize for value hint to always push the optimizer to produce that kind of plan. Now, all of these have different degrees of friction in order to implement them, and they all have their drawbacks in terms of implementation or use or maintenance. So we're introducing PST optimization. And the idea is that PST optimization is going to work well with other intelligent query processing features and with automatic tuning and with plan forcing. By analyzing these parameter-sensitive plans, we are not creating additional overhead, so the presence of this feature must not outweigh its benefits. And what it will do is automatically create multiple active cached plans for a single parameterized statement. So in essence, the scenario that we've just seen will in fact be handled by different plans that will both be active in the cache, depending on the incoming statement parameter. The cached execution plans will try to bucketize, accommodate different data sizes, and this is based on the incoming runtime parameters. These need to be supported by statistics that we will use. Remember what we discussed for cardinality estimation process. And based on that, we will be able to identify buckets that will require different plans depending on the incoming parameter and create those plans and put them into cache to be used as needed. Now, how is that predicate selection done? During the initial compilation of the first time that query is executed, we will evaluate the most risky predicates, up to a maximum of 3. And based on those at-risk predicates, we'll create those, let's say, buckets, or identify the possible different plans that could be used, depending on the value. And that's used using the column statistics histograms that are there and allow us to identify non-uniform distributions. This first version will only cover equality predicates, something like where agent ID equals the parameter agent ID. Here's how some concepts change when you look at PSP optimization feature. We'll have the notion of dispatcher plans and query variants. Consider a dispatcher plan is an abstraction that contains a logic, we call that the dispatcher expression, that will then map to all the possible query variants, and the query variants are pre-identified based on the cardinality estimation for each of the potential parameters used, identified from the histograms that were available to us on those columns that map to equality predicates. The dispatcher plan is built during the initial optimization, and because in the initial optimization you already have one parameter that you are requesting the query to be executed with, the first query variant will be immediately available. So think of a query variant as the actual plan for a given bucket of incoming parameters. So each query variant will be its own execution plan in the cache. It can be differentiated in the query store. So each query variant will have a different query plan hash for the same query hash. And so you are able to identify if you have multiple active plans for the same parameterized query. These plans, so these query variants, will be able to be independently recompiled as needed. So the default recompilation thresholds for any given query plan do not change even when applied to these query variants. If there is a schema change, if some statistics change the data distribution, maybe all the query variants need to be recompiled, maybe only some of the query variants need to be recompiled. That new compilation of a query variant or recompilation of a query variant, just like any other query, will happen only when that given variant is called on. Meaning, in the first execution, we calculate the dispatcher plan, and we calculate the first query variant, the first plan produced for the incoming parameter. At that point, we've already identified through looking at statistics what potential other plans may be used, or in other words, what potential parameters are linked to different data distributions that may be using different plans, but only when those respective parameters are called on the first execution, we will create an actual plan for those. So we will not incur the overhead of creating query plans, query variants, for all the potential incoming plans at the first execution of the first one. It's only at the first execution of each, let's say, bucket value. So one picture speaks more than 1,000 words, so here's our attempt to do that. There's an incoming parameterized query, one dispatcher plan is created. The first agent, let's say agent ID 2, had less than 10,000 listings. It works well with the seek and the lookup and the small memory grant. We have another query variant that returns more than 1 million rows. That needs to have a scan and a large memory grant. We even identified a few that are between 10,000 listings and 1 million listings that can also leverage the scan, but maybe only a medium memory grant. These calculations are done through the dispatcher plan, but the actual plans that bring these to shape that will then be used to execute any given variant are only created on the first call of a parameter that fits into each of these buckets. Let's look at a demo for this feature. For this demo, we are using the property MLS database. This is a database for a real estate company, and it has tables with agents, so real estate agents with their IDs, and also a table with properties, listed properties for sale. We'll set up the query store. Again, very aggressive settings for a demo purpose. This is not to be used in production. And this is a feature that also depends on the query store being enabled, which is a default in Azure SQL database. Just ensuring that we have a clean demo environment. This trace flag is only now because I'm showing you something that it's not in public preview yet. This will not be the case when we reach public preview. And so let's look at the property search by agent store procedure to see what we'll be executing. And so this store procedure takes an agent ID parameter, and using that agent ID parameter, it will return data from the property table for that agent ID, and it will order the result set by listing price in descending order. So let's look specifically at the predicate. It's on the column agent ID. Now, I have previously searched which statistic object has the agent ID column, and I know that it is the statistic created for the non-clustered index property agent ID. So let's look specifically on that histogram to try to determine what data distributions exist inside this table specifically for the agent ID column. This is basically what will happen, what will be used by the PST Optimization feature to determine the possible variants, the query variants that may exist for this parameterized query. So we see that there are a couple of range high key values, agent IDs 1 and 2, that have almost 5 million rows each. And then we have a number of agent IDs that have a few thousand. And we have also a high number of agent IDs that are in the low dozen or low hundreds. And this is fairly recurrent throughout the histogram. So we have a fairly even distribution of a few thousand to just a few hundred, or even a few dozen. And we have these two, 1 and 2, that are significantly skewed in this data distribution. All right. Now let's execute this store procedure first with agent ID 2. The default behavior for SQL Server without this feature would be that the first execution of this store procedure, of this parameterized query, and the plan that would be created for it would be cached, and that would be the only plan going forward for any call to this store procedure until such time as it recompiled. So let's execute this with agent ID 2. So the query is completed, and through the magic of time-lapse, we didn't actually use these last almost 2 minutes in the video. Let's look at the execution plan. And we see that we have a cluster index scan, a sort, and that is a plan that is deemed good enough to read and to present this almost 5 million row result set, as we see here. So accurate estimations. There is a sort warning here that we see it's a spill. This, as we executed additional times, would be taken care of by memory grant feedback. And let's look at the properties to see the query time stats here. So we see that we used almost 40 seconds of CPU and around 105 seconds of elapsed time. All right, then now let's execute with values of agents that have fewer properties. We'll execute this one 4 times and this one 8 times. So again, by default, without this feature, these executions with agent IDs that I know have less properties would still use a cluster index scan with a sort on top. Now that we have enabled PST optimization, let's see what happens when I call these executions that have a lot less rows being returned. So I see that the execution is done. It was much faster. And as I look here, I see, for example, that for agent ID 4, we use a very different plan with the nested loops, and the sort is still here as expected. This is so cheap that it didn't require to go parallel, so it's a serial execution. And we see throughout other executions, even this one, so this is the third, they all use the same plan. So there's no significant differences between 8 and 4 in number of properties, so they fit into the same query variant, which again is using a nested loops and an XSeq and a key lookup with a sort on top. All right. If we look at the execution time, obviously we've noticed that it's much, much faster. It's not even 1 millisecond of CPU. It's not even 1 millisecond of execution time, which is great. All right. Now let's look at the cached plans for this store procedure. And indeed, I see 2 plan handles. We're looking at the cached plan. So we see 2 different plan handles, one with 1 use count, and this is for agent ID 2. And then we see 6 use counts for this other plan, which is the 3 executions with 4 and 8 agent ID respectively. And this is indeed the query that I was running. So here is the proof is in the pudding, like they say, and here we can see that we have indeed 2 cached plans for this same parameterized query. I can even search in the query stats and see additional information. For example, I see here the query plan for both. I see the SQL handle is different, but what I want to really look at is the query hash and query plan hash. So as I discussed earlier, this is, as expected, the same query hash, because it is indeed the call to the same store procedure. But we can see there are two distinct query plan hashes, both for plans that are currently active in the cache. We can see that for this plan that we executed once, we see the number of rows that were returned. We see for this other plan how many rows were returned overall, and the last time this was executed, just 9 rows were returned, and the minimum was 3 rows at some point in time during the 6 executions that I ran. So indeed, we can see here that we have different plans in cache. They are both active, and these query variants will be used depending on the incoming parameter that maps to that given query variant. And if we look in the query store, we'll also see this data reflected there. For example, using the top resource consuming report, if I go into tabular format, I see here that query ID 2, I see the total duration is the 105 seconds, almost 40 seconds of CPU. And I see here that this is the plan that we've seen before. And the other variant is now captured as query ID 3, as you see here. And it also captured its specific performance data in the query store separately. So both in the cache and the query store, these two variants are treated as expected as two different plans and two different query IDs in the query store. As I mentioned, this feature will be in preview in Azure SQL Database later this year. Follow the Azure Update blog to stay tuned for more preview announcements. And if you have any feedback about this feature, you can use that email to reach the team. Thank you very much for your time today. Hope you enjoy the rest of the summit and enjoy your day.